The problem we'll be dealing with today is the characterization of RF networks and how radio frequency engineers use something called scattering parameters to analyze such devices. In order to understand what is meant by a network, let's consider a two-port device as an example. Although this circuit may consist of a variety of electronic components, such as resistors, capacitors, inductors, and other passive or active elements, S-parameter measurements treat networks as black boxes, regardless of how complicated the underlying circuitry is. Suppose we excite a power wave of some frequency at port 1. We'll refer to the incident wave as A1, to the transmitted wave measured at port 2 as B2, and to the reflected wave measured at port 1 as B1. Similarly, we can excite a power wave at port 2 and measure the energy of the signal emerging from both ports. As you can see, upon the excitation of a signal, energy is distributed, or scattered, among the ports of the network. Let's assign some names to these signal paths, or, as we'll soon be referring to, S-parameters. You might be wondering, how exactly do these subscripts get named? Well, the notation for scattering parameters is pretty straightforward. The first subscript corresponds to the output port, where the energy emerges, while the second subscript corresponds to the input port, where the incident wave is applied to. Of course, this notation applies to networks consisting of arbitrarily many ports. Let's take a closer look at how the incident power wave, A sub I, is defined mathematically. The incident wave equation involves the complex amplitudes of the voltage and current at port I, as well as the complex impedance of the port. Similarly, the reflected wave B sub I depends on the same factors, except the impedance is now substituted for its complex conjugate, meaning the resistance remains the same, but the signs of the reactance is flipped. The Ki coefficient, present in both equations, is equal to the inverse square root of the absolute value of the real part of the impedance. To better understand what this means, let's head over to the complex plane for a quick refresher. Remember that impedance is a complex quantity, consisting of a resistive real part and a reactive imaginary part, which, depending on its sign, is either inductive or capacitive. The magnitude of the impedance can be directly computed using Pythagoras' theorem. The phase angle phi, describing the phase shift by which the current lags the voltage, is given by the inverse tangent of the ratio of the imaginary part to the real part of the impedance. Going back to the equation for the Ki coefficient, it is now evident that the real part of the impedance simply refers to the resistive component. If the ports of the network all share the same impedance, which is usually the case, Zi can be replaced by Z0. So let's substitute this coefficient back into the power wave equations. We can now relate the output with the input by simply attaching a coefficient. The relation between the incident and transmitted or reflected waves can be expressed using a square matrix known as the S-parameter matrix. This matrix consists of n squared elements, where n is simply the number of ports of the network. In the case of a two-port device, for example, the S matrix consists of 4 elements. By defining the incident voltage wave as V+ and the emerging voltage wave as V-, we can transform the scattering matrix and define S-parameters as the ratio of V- to V+. Remember that, because we're dealing with complex quantities, S-parameters are complex values, consisting of both amplitude and phase, although in many applications the most interesting quantity is usually the magnitude. Now that we've covered the fundamental theory behind S-parameters, let's try to examine and interpret what is actually going on inside a network upon the instance of an input wave. If the two ports are perfectly matched, the signal will not stumble upon any discontinuities or mismatches, and no amount of energy will be reflected. Therefore, the magnitude of S11 will be equal to 0. On the other hand, since 100% of the energy is transmitted to port 2, the magnitude of S21 will be equal to 1, or 0 decibels. We can visualize the uninterrupted flow of energy by observing the electric field in a so-called through transmission line, where no discontinuity is present between the two ports. Now let's see what happens when we introduce an impedance mismatch by setting an impedance Z1 that is not equal to the conjugate of Z2. As soon as the wave meets the discontinuity, we can observe partial transmittance and reflectance. This yields a magnitude of S11 greater than 0 and S21 less than 1 or 0 decibels. If we head back to the E-field visualization, it is obvious that the introduction of an intervening trace, representing an impedance mismatch, reflects a significant amount of energy back to the incident port, while considerably attenuating the amount of energy transmitted to the output port. But why does the energy on the left appear to oscillate instead of simply traveling backwards? To properly understand and interpret this observation, let's examine what happens when a reflected wave meets an incident wave on the same position along a segment of the transmission line. Let's begin with the incident wave in blue, and add the reflected wave in red, whose amplitude will be slightly lower than the incident wave's amplitude. The resulting wave in green will be the sum of the incident and the reflected wave. As you can see, when the crests of the waves meet, the resulting amplitude is high, leading to constructive interference. Whereas, when the crests are aligned with the troughs, the resulting amplitude is low, leading to destructive interference. We can quantify the so-called voltage standing wave ratio, or VSWR, by simply taking the ratio of the maximum to the lowest voltage in our standing wave. The standing wave ratio is simply one way we can express the level of reflection in a network. Now that we've understood the fundamentals surrounding S-parameters, let's take a look at how they are applicable to a few example networks. Starting with antennas, since we're only dealing with a single port, the scattering matrix consists of just one element. If we plot the magnitude of S11 as a function of frequency, we can observe that very little energy gets reflected at 2 GHz. This is usually a reliable indicator that our antenna is well matched at this particular frequency, transforming between electromagnetic radiation and electric currents effectively. Another example of a single port network is a dummy load. A dummy load typically consists of a single or a set of resistors specifically designed and intended to match the source impedance of the system. If the dummy load is perfectly matched to the impedance of the source, virtually no energy will be reflected, as it is all dissipated in the form of heat. Keep in mind that, as we'll see in the following examples, we can also use these electronic symbols to imply a common impedance between ports expressed in terms of a source and termination load. Let's take a look at a two-port network, like an LC filter consisting of an inductor and a capacitor. Since 2 squared is equal to 4, our S matrix will consist of 4 elements. Let's begin with the transmission coefficient, S21. As you can see, this particular filter lets low frequency signals through with very little loss, while significantly attenuating higher frequencies, specifically beyond 3.5 GHz. Since this is a reciprocal network, solely consisting of reciprocal elements, S12 will be identical to S21, and so will the reflection coefficients S11 and S22. Even though the reflective filter we just studied conserves energy in the form of electric currents being transmitted and reflected, there are also lossy networks like attenuators. These passive devices absorb a significant amount of energy while introducing loss across a wide frequency range. This particular pi-pad attenuator provides a loss of approximately 15 to 20 decibels. A circulator is a passive device that achieves something quite interesting. It typically consists of 3 ports, giving us 9 scattering parameters. The amazing property of this non-reciprocal network is its ability to pass signals around the ports in a circular one-way direction, exactly as the scattering parameters demonstrate. To visualize how the energy flows from one port to another in a circulator, let's take a look and monitor the E field, beginning with the excitation at port 1. As the incident wave interacts with the non-reciprocal ferrite at the center of the device, its energy is almost entirely directed to port 2 by the ferromagnetic properties of the ferrite. Similarly, if the signal is excited at port 2, it will arrive at port 3. Finally, if the incident wave comes from port 3, the signal will be directed to port 1. At this point, let's once again consider a circulator, but instead of having a 3-port network, the third port is now terminated with a matched load. This modification introduces the effect that any signal entering port 2 will be absorbed by the network, making the implementation of this device ideal for applications where reflections are strongly undesirable, such as the input of a filter or the output of an amplifier. Although the networks we just studied are all passive, it is worth noting that there are also active networks that can be characterized using S-parameters. One example of an active network is an amplifier, whose role is to introduce a level of gain to the input signal, leading to an amplified output. Of course, due to the conservation of energy, such operation is physically impossible without an external source of energy, such as a DC current. If we plot the scattering parameters of this 2-port device, you'll see that S21 provides the amplification gain as a function of frequency, and by looking at the reverse isolation, or S12, we can immediately tell it is a non-reciprocal device. Lastly, the reflection coefficients S11 and S22 describe the input and output return loss respectively. At this point, it is worth mentioning that the scattering matrices of certain types of devices may vary depending on a number of factors. For example, if we adjust the DC voltage providing power to our amplifier, the S parameters are slightly affected. Likewise, as the physical temperature of the amplifier increases or decreases, its characteristics are influenced in a similar manner. In other words, the scattering matrix is often a multivariable function involving parameters like the supply voltage and physical temperature, and in the case of nonlinear circuits, even the input power. Now that we've got a solid understanding of how networks can be characterized using scattering parameters, it is useful to know that we can sometimes refer to S-parameters by certain names. For the reflection coefficients, where I is equal to j, that is, the elements that lie on the main diagonal of the S matrix, S11 and S22 correspond to the input and output return loss respectively, both of which can be expressed in terms of the VSWR. As for the transmission coefficients, S21 represents the gain or loss across a network, while S12 can sometimes describe the reverse oscillation between 2 ports. Let's talk about 2 meaningful characteristics a certain network may possess. If the scattering matrix of a device is equal to its transpose, the network is said to be reciprocal. In other words, Sij equals Sji. A network is considered lossless if it does not absorb any of the input energy. In other words, the total power transmitted across and reflected by the network is equal to the total incident power entering the device. Remember that because power is proportional to the square of the voltage, if the sum of the squared S parameters for each column in the S matrix is equal to 1, no power is absorbed by the device, and the network is said to be lossless. Finally, let's look at how the reflection coefficient is related to the voltage standing wave ratio that we previously studied. The quantity gamma represents the voltage reflection coefficient, which is determined by the load impedance, Z sub L, as well as the characteristic impedance, Z naught. This is equal to the ratio between VSWR minus 1 and VSWR plus 1, which is easily proven from the derivation of Vmax and Vmin expressed in terms of the forward and reflected voltage waves. Hence, the magnitude of S11 is simply that ratio expressed in decibels, and if we plot each quantity against each other, we can see that as the VSWR approaches infinity, S11 tends to 0 dB, and as S11 approaches negative infinity, the VSWR tends to unity. In conclusion, S-parameters are a great tool for the characterization of a variety of electrical networks, particularly at radio frequencies, and they are frequently applied in fields like telecommunications engineering, radio astronomy instrumentation, and RF engineering. Although scattering parameters were originally introduced over half a century ago, they remain highly relevant today, and are being used to examine devices using instruments called network analyzers. Thanks for watching.